we are going to solve an AC circuit using complex numbers. The circuit we are going to solve today consists of a capacitor, an inductor, and a resistor. We know the values of the capacitance, the inductance, and the resistance. We also know the RMS value of the voltage applied and the frequency. We are asked to calculate the equivalent impedance, the RMS value of the current to each element, and the active, reactive, and apparent power. We start solving the problem by calculating the reactive capacitance and the inductive capacitance using their respective expressions, 1 over omega C and omega L respectively. We find values of 15 ohm for the former and 30 ohms for the latter. We now introduce complex numbers. We write XC as a complex number with no real part and a negative imaginary part. We write XL as a complex number with no real part and a positive imaginary number. And finally, the resistance is a real number. Notice that I'm using the notation J instead of little I to avoid confusion with the symbol for electric currents. From this point on, until the end of the problem, we treat this AC circuit the same way we treat DC circuits. We first find the equivalent impedance for this portion of the circuit using the same expression that we normally use to find the equivalent resistance of resistors connected in parallel. This equivalent impedance of the RL part of the circuit is connected in series with the capacitive reactance. Therefore, in order to find the total impedance of the circuit, we simply add these two quantities. We find the impedance in complex form, 14.4 plus 4.2 J in units of ohms. And to find its value, we calculate the modulus of this complex number. We find a value of 15 ohms for the total impedance. To find the RMS values of each current in the circuit, we first notice that the current to a capacitor is actually the total current of the circuit. That is due to the position of the capacitor in the circuit. Applying Ohm's law and keeping in mind that the voltage is a real number, we divide the voltage, 100 volts, by the impedance in complex form that we just found, and we obtain the value for IC, both in complex form, and again, its value by calculating the modulus of this complex number. Continuing our parallel treatment of this circuit with DC circuits, we write Kirchhoff's law for the junction and Kirchhoff's second law for the loop. We end up with a system of two equations with two unknowns, IL and IR. Solving this system of equation is relatively straightforward. So we find IL and IR, again, both in complex form, and their magnitudes by calculating the modulus of each of these complex numbers. Finally, in order to find the power, we recall that for a DC current circuit, the power is current multiplied by voltage, or current squared multiplied by resistance, or voltage squared divided by resistance. For the problem here, perhaps the most convenient expression to use is I squared R, or better said, the equivalent expression of I squared R. The reason for that is that we know all the currents and we know all the elements of the circuit. The active power is the current to the resistor squared multiplied by the resistance. The reactive power is the sum of all the I squared multiplied by X terms to all the capacitors and inductors in the circuit. Again, recalling that the capacitive reactance is negative and the inductive reactance is positive, while the apparent power is the total current to the circuit squared multiplied by the total impedance. We find that active power is 640 watts, the reactive power is 190 VAR, and the apparent power is 670 volt ampere. A good consistency check for such problems is to see if the sum of the voltage drops around the circuit is equal to the voltage provided by the source. Indeed, applying Ohm's law for the capacitor, we find that IC multiplied by XC if we add it to the current to the resistor multiplied by the value of the resistance, if we add these complex numbers together, we obtain a real number, 100 volts. And this is exactly the RMS voltage provided by the source. Therefore, we confirmed that going around the loop, the sum of the voltage drops is equal to the voltage provided by the source, as expected.